Okay, so we have seen applications of methods in one field and from one field in other fields, which are seemingly unrelated. And often that leads to exciting results. For instance, convex integration techniques applied to PDEs from geometry. Okay? And we have discussed that a lot in this program. What I'm going to talk about today has kind of this flavor as well. We have two topics here. One is a mathematical topic. It's the regularity problem for the three-dimensional Navier-Stokes equation, the supercritical case. Another is a physics topic. That's the Kolmogorov's turbulence theory, which is phenomenological. Okay. The main message I'm going to deliver here is that, inspired by some physics laws here of Kolmogorov, we obtain a new regularity criterion for the 3D Navier-Stokes equation, which improves many classical results in the literature. Okay. Not only that, but also we are able to justify some physics laws here rigorously. Okay. All right, so let's start from Navier-Stokes equation here. So we have an important parameter nu, that's the viscosity coefficient, incompressible, so divergence free. And we consider the Navier-Stokes torus. The relevant dimension is either 2 or 3. Okay. And from the perspective of mathematics, the central question we care about is the well-posedness, or let's say global well-posedness. Okay. Solutions. And when we talk about solutions here, there are different solutions: weak solutions, regular solutions, strong solutions. And well-posedness is in the standard sense, existence of solutions, right? And uniqueness and continuous dependence on the initial data. The last one sometimes can be thought as a stability problem. Okay. In general, here in 2 dimensions, this problem is very well understood. And in 3D, the understanding is very limited. Although many generations, mathematicians have been working on the 3D Navier-Stokes equation. Okay? And here I'm going to show you a very simple way to say why the 3-dimension case is much harder. Okay? 2 simple facts. One, it's the energy law satisfied by the equation. And a priori that gives us the estimate of infinity of 2 and 2 space-time. So the first one gives us this, and this term dissipation gives us the entropy. Okay. Second, the natural scaling satisfied by the Navier-Stokes equation, namely so if the pair U and P satisfy the Navier-Stokes equation, then you rescale to this way that your lambda to lambda satisfy the system as well. Okay, under such scaling, there are scaling invariant spaces which are called critical space. So here, right from the scaling, we can get the largest critical space. That's the best of the space. Okay. So that's the largest one. Since we are going to use the concept of Littlewood-Pelly theory quite often, so I'm going to explain you what is the best of space here. Okay. The norm. So the norm is given by a Qth shell. I'm going to explain to you just in a second. On the Qth shell, you look at this index, that's our infinity norm, and here that corresponds to the degree of the derivative. And that last index is the little LP. Since it's equal to infinity, we take supranorm here in Q. Okay. So that's the norm of the best of space here. This index of a derivative, it comes right away from scaling here. Okay, so what is the Littlewood-Pelly projection onto the Qth shell, right? So we look at a bound function, which is the Fourier transform of which. Okay. So there is a phi Q. The Fourier transform is supported near the 2 to Q. So basically here, Q minus 1, and there 2Q plus 1. Okay. And you take the U convolution with this phi Q, and that is the UQ. Okay. So when you look at the Fourier transform of a UQ, it's only supported near this frequency. Okay. And by Littlewood-Pelly's theory, that's a partition of U, okay, in the distributional sense. All right, so here, that's the best of a space. And this one, again, it's the largest critical space for Navier-Stokes equation, and it's independent of dimension, okay? In any dimension, that's the largest one. Okay, so now let's actually look at other critical space, other critical spaces in 2D, just by using Bernstein's inequality. Okay, so we take this largest one, the smallest norm. We can change the LP to any other LP. For instance, let's look at L2. Then by Bernstein's, here it's in 2D, so 2 times this half gives us 0. So that corresponds to the space L2. Okay, so L2 is critical for 2D Navier-Stokes. And let us zoom in, for example, and look at in the 3 dimension. Change it to L2 based. So now it's in 3 dimensions, 3 half. That gives us a half. Okay, that corresponds to the space H half. Okay. Okay, so H half, it's a critical space for 3D Navier-Stokes. Another one I want to mention is the L3 based. So use, so here I want the L3 based. Then it's 3 dimension and 1/3. That gives us 0. Corresponds to L3. So in 3D, we have these 2 very special critical spaces. Okay. Okay, so now when you combine the 2 pieces of information, you notice that in 2D, the energy space is critical, and that's good. Okay. So basically, you can get a regularity by bootstrapping. Okay. So because and the priori energy law gives us the critical space here. However, in 3D, the critical space, H1/2, we don't have such a private estimate. What we have, it's L2. So in 3D, L2 is supercritical. It's not enough to bootstrap to get higher regularity. So here, that's a very simple way to think about it, why the 2D is easier and 3D is much harder, okay? All right, so next, I'm going to focus on the 3-dimension situation and talk about the well-Poisson's, global well-Poisson's regular solutions. And that's the global regularity problem for 3D Navier-Stokes equation. And of course, it's open, and what we know is some partial results or conditional regularity results. So let's go from some classical regularity criteria in the 3D case. Okay, so here there is a large area of study conditional regularity results, meaning that you give some additional constraint, and with that constraint, the solution is guaranteed to not blow up. Okay. Some classical results goes back to 47. Around this time. The condition is that if U is in this space, satisfying the condition. So if U is in this space, let's say here up to time 0 to t, then this t cannot be a blow up time. Okay, this quantity is a scaling invariant, it's critical space. And you note that the condition here, s equal to 3, is not included. Okay, so that's the ending point. However, it's actually true, it's just the proof came much later. The ending point is much harder. So here, the proof was given by Escariza, Sarabian, and Schwerik. Around this time, so you can see the gap, 40 years to get the ending points. Okay, so they showed that indeed, if U is in this ending point space here, again, it's good. Okay, no blow up. Okay. Another classical condition is given by Bill Caldwell. This time, it says that you look at the vorticity, L infinity norm, if it's integrable, then this t cannot be a blow up time. Okay, and there is a improvement of BKM by Conditional. It says that the information is too much. We don't need that much. Just look at the shell. Infinity norm. Look at the integral near a potential blow up time. We take sigma in the shell, take the limit in epsilon. If this quantity is small, then t is not a blow up time. Okay. Again, so those quantities they have the same scaling, but they are scaling invariant. Okay. Okay. So those are the classical results, and of course, there are many generalizations of these classical results in different species, okay, but with the same scalings, of course. And recently, we obtained a new condition. It says that that's too much too. We don't need that much. So we just need the vorticity, but with restricted low modes. I'm going to explain to you what is the Q, okay? It says we just need to look at low modes, okay? And integral near a potential time, let me soup in Q, that is smaller than T is not block time. This is a joint work with Alexei here. So here, this Q, it's the Q shell, the capital Q is defined. Minimum of wave numbers is satisfied. Then a small constant, C naught. So that's how the wave number defined here, okay? And then the whole condition, it says we just need to look at the one shell of vorticity, but restricted to low modes. Okay, if that quantity is bounded small, then we are good. This wave number was introduced by Alexei and Roman earlier in early previous result, previous work. Okay, so some remarks about this condition. Let me call it star. Okay. So we showed that.
So let me just understand. So you're fixing a C naught?
Yes, it's
right,
a small.
So it's the same C naught as the C naught above.
Yes, that's right. Okay, so we showed that this condition is weaker than the classical ones, protoserum, BKM, and Plechon. And regarding the ending point, it's tricky. So at the time when we wrote the paper, we didn't know whether this condition and the other three conditions, one of them implies the other. We didn't know. Okay. Proved that the wave number here is bounded by the three norm triple exponentially. And it's a highly non-trivial. And as a consequence, it says the condition we have here is weaker than the ending point situation as well. Okay, so then so that's Vladimir's result here. Okay, so basically with the help of tau, the picture is complete. This condition, it's weaker than all of these classical ones. Okay, and we kind of have the feeling that this condition, possibly we have pushed it to the limit from the positive side without breaking the scaling. So any further improvement might require breaking the scaling. Some interesting questions left here. So it would be nice to have a better understanding on the dynamics on the wave number here, which depends on time. And we know that when a solution blows up, this wave number has to blow up as well. So we like to know the optimal or the sharp growth rate of the wave number when solution blows up. Okay. Okay, so near that time t, what's the growth rate? What's the sharp growth rate? And of course, those questions are not easy. You can see from here. This work it's very technical, and the bound is intra L3. Okay. Yeah.
So the two things combined actually gives you a proof of the regularity for L infinity L3, which is not using any unique continuation argument. Tau uses actually the unique continuation argument of the Navier and
wait a second. No.
So tau use a different method.
Right. So the two things combined is not using any blow up techniques, like any descaling techniques like you're using studying the unique continuation problem for solutions of.
Right. I don't think so. Right.
It's purely Fourier.
Right. What we did here is
So it's purely Fourier, and it's purely analysis Fourier even for the other side.
He uses quantitative unique continuation, so it still has that element to it.
Okay. So it's still using unique continuation in some other form though.
Well, in fact, it's almost the same Kalman estimates.
Okay. Okay. So you don't really get rid of that idea after all. Yeah. Okay. Thanks.
okay. Okay, so now about the ideas behind the criterion star condition here. So we were inspired by the Kolmogorov's turbulence theory, the physics course. So now let me briefly recall the P41 turbulence theory. So roughly saying, there are three predictions here of phenomenologies. First, there exists a critical wave number called kappa d, such that modes below this wave number, they are essential to describe the flow. That means that modes higher than that are dominated by dissipation force. Okay, and by dimensional analysis, there is a scaling for this wave number. Epsilon here is the average dissipation rate. So the bracket denotes time average. Second, below this wave number, there is this energy spectrum scaling. It's the famous -5/3 law. So in K, it's less than the critical wave. Okay. Third, it's about the average dissipation rate. This epsilon does not converge to 0 as the viscosity goes to 0. Okay. So all of the three are phenomenologies. This one is actually a major open problem. Okay, it's a conjecture, the anomalous dissipation. So if I draw a picture here, with number k, here it's a log, the energy spectrum, okay. There is a critical wave number here. Below those, we have this a straight line with a slope -5/3, and after that, its dissipation goes down very quickly. Okay, and this wave number converges to, based on this scaling infinity as nu goes to 0. Okay, so here, first one says that the kappa d separates initial range from the dissipation range. Second, it says in the initial range, energy distribute according to the wave number by this scaling. Okay, and the last one says there is anomalous dissipation. Okay? And the one that is relevant to a regularity problem is clear. It's this one, right? Okay, so it says only the low modes matters, the high modes don't matter. Okay. However, we can't use it directly, right? We can't use this directly in our proof. We have to find a mathematical analog of such wave number in our context. And how do you find such analog? So the heuristics is that the difficulty really it's about the competition of the nonlinear term and the linear term. So then let's just look at the two and compare them. For instance, that's the nonlinear one and that's the linear one. And we just look at the other two known. And to make it simpler, we just look at only shell. Okay. And by Bernstein's, first order, okay. On the shell, so gradient it's a lambda cube, infinity, and and this one Laplace gives us a square of lambda cube. So lambda cube is the frequency. Okay, just notation. Say if we want the nonlinear term to be dominated by the linear one, so let's say we want the inequality in this direction, then let's cancel this, and that gives us it's exactly the quantity appeared in the definition of the wave number. Okay. Yeah. So of course here just everything is just heuristics, and we have to make it rigorous. Okay. But I'm not going to talk about the proof. So now when we look at this condition and the ideas behind that, it seems that, of course, this physics law makes sense, right? And then we ask the question, can we actually justify the physics law rigorously? Okay. And that's the second part. Here we focus on the prediction one. If we have time, we'll talk about the 2 and 3 as well. Okay. So just find the criticality of the Kolmogorov dissipation wave number. It's closely related to another classic topic here, determining modes, which is related to the topic of finite dimensionality of global attractor and number of degrees of freedom flows. Okay. So some background here on the topic of determining modes. The study was initiated by Affiliation. They studied 2D flow, and then they showed that high modes asymptotically controlled low modes, meaning that if there are two trajectories on the attractor and they coincide below some modes, then they are identical actually on the global attractor. Okay, so again, the high modes are dominated by the linear term. Okay, those low modes are called determining modes. Okay, and the number of determining modes was estimated by Jones and TT. So again, it's a 2D case. Modes is bounded by the Grashof constant, and I'll explain to you. The force. So here we consider the problem a 2D torus. The force, okay. The size of the torus is 1. Okay, so that's the Grashof constant. Okay. In 2D, again, we know that solutions are regular, so we have bounds on higher norms. Those results were obtained by classical energy methods. Okay. However, in 3D, the situation is much harder since we don't have global regularity. But there was a partial result, okay. Conditional result by Affiliation. So that's like 1983. So those are really very old results here. So in 3D, assume the H1 norm is bounded, then they showed the existence of determining modes, and they estimates of on the number of determining modes in terms of the higher norm. When you look at this condition, it's rather strong. That's basically assuming regularity. H1 is a subcritical norm. Okay. Okay. So in the 3D case, for Navier-Stokes equation, it was out of reach to study the problem of determining modes without assuming regularity. Actually, it's hard for any supercritical equations. Okay. So a few years ago, we started to look at this problem together with the regularity problem, and we realized that there's an intrinsic connection between regularity of solution and intermittency effect. So we developed a new approach, different from the classical energy methods. Okay, so we developed a new approach to treat supercritical equations by taking into account of intermittency effect. Okay, so now maybe let me introduce the notion of intermittency quickly. So after the K41 theory, there were experimental studies which showed the deviation from the classical scaling. And such deviation it suggests that there are fractal structure at fine scales of the dynamics. And it was captured by the notion of intermittency. Physicists, they introduced intermittency, okay? And they have a physics notion, D. It's a fractal dimension to measure the intermittency level, okay? And then with the correction of intermittency fractal dimension here, the scaling of the kappa D is given by here, and the energy spectrum is given by. Okay, so you can see that here the fractal dimension is from 0 to 3. So when the dimension is 3, that's the classical K41 region. Okay, so that is 1/4 and -5/3. Okay. Okay, so yeah, we're going to use intermittency in our analysis. However, again, we can't use this physics notion. We need our own notion, more let's say precise or quantitative notion for intermittency. So here we are going to introduce a mathematical notion of intermittency. So we look at a vector field on torus, 3 dimensional. Okay, and we look at 2 norms, the L-infinity norm and L2 norm. Take the time average and compare the two. And we are going to put a parameter S here. Less than a constant that depends on the parameter S and the size of the tones. Okay. For such as satisfying this inequality, we take the supernorm. Supernorm such as, and that is our definition for intermittency. Okay, and I'll explain you why we choose it this way and why it makes sense. So let's start from this quantity. Okay, L2 squared. Yes. Okay. And the beholders, we have lambda q and uq infinity, right? Okay, so here it is holder, okay, and this one is Bernstein's. In 3D. So L2, it's 2 times 3 halves. So that gives us 2. Okay. So now we look at the comparison of L infinity norm of a shell with L2. That's the scaling. That's the lower and upper bound, right? -1 and 2. So we add a parameter here to saturate this inequality, and that is our intermittency. And we can show that it's from 0 to 3. That's the intermittency dimension D. When D is 0, that's the extreme case. So it's corresponding to something highly concentrated. So like this. The length scale is 2 to Q negative. Okay. And when the intermittency dimension is 3, that's the Kolmogorov classical regime. It corresponds to something more smooth and irregular. And the length scale is lambda Q, 2 to negative Q. Okay. So basically, the intermittency dimension, it corresponds to the regularity level of the flow. When D is 0, it's the most irregular situation. So only one eddy occupies the whole regime. And when D is 3, that's the regular situation. Okay. Okay, so now with this preparation, we are going to design wave numbers, which we are going to show that they are determining wave numbers. And hence we have determining modes. Moreover, we are going to show that the wave number we design has a bound from above by the Kolmogorov dissipation wave number. Okay, so I'm going to explain details. Okay. So first, let me give you the wave number. Okay. We call it determining wave number. So for 3D Navier-Stokes equation, we do it in 2 separate cases. When D is 0, the extreme situation, and when D is away from 0. Okay. In this situation, we take wave number. It's defined as minimum of wave numbers satisfying 2 conditions. Here, P R. Q, and one more condition on low modes. And infinity here the R cannot be anything. It's from 2 to 3. Okay, so here we impose 2 conditions. One is on the high mode, that's in terms of a critical norm of R. Another is it's a condition on the low mode. If you move the nu to the left hand side, you realize that's the Reynolds, right, on the low mode. Okay, so anyway, that's a wave number we designed, and we showed that The wave number we have there, it's a determining wave number. Okay. In the following set, we have 2 weak solutions. And for each trajectory, we have a based on that definition. We take the maximum of the 2. And if the 2 solutions are restricted on the low modes, okay, so below this wave number coincide, then show that in the energy space, asymptotically. Okay, so that's what we mean by determining wave number. It's in the same sense as determining modes. Okay. Okay. Second, the wave number we define there, its time average is bounded above by the Kolmogorov dissipation wave number, and precisely, okay. Again, it's optimal. The power is 1 when the intermittency is 0. Okay, we have bounds for all of the other intermittency range, but it's not optimal. It has a power. It has a power larger than 1. But in this extreme case, it's optimal. Okay. Okay, so this one, it justifies the Kolmogorov prediction 1, but in the case with extreme intermittency dimension. Okay, and for other regimes, when the intermittency dimension is away from 0, we have another wave number. Against determining wave number, and in the case D is not 0, it's away from 0, intermittency dimension. Okay. Okay, so here we are going to use, so earlier we used R norm, and R is rather small. So here we're going to use our infinity norm. That's the largest critical space and the smallest critical norm. So it's supposed to give us better infinity. Okay. So we couldn't just use this directly because that won't give us optimal result. Instead, we need to use the L-infinity scaling, but optimize things with a kernel. Okay. So parameter eta. And condition on low modes as well. And here we need to take a bit by adding a gradient here. Okay, and such a wave number satisfying the 2 conditions will take the minimum. Okay, so here we use a different critical norm, the smallest one. Okay, and we showed that. Again, this one is a determinant wave number in the same sense. Second, the time average is bounded above by Kolmogorov wave number. All of the D away from 0. Okay, so again, the estimate is optimal. Okay, so that is exactly what is predicted by Kolmogorov. Okay, so what we did here, two things, right? So first of all, we developed a way to treat supercritical cases when we study the determining modes and determining wave number problem. And the second, we justify the Kolmogorov prediction 1 on the criticality of the Kolmogorov dissipation wave number for all of the regime of intermittency. And our wave number, the results has no assumption on regularity. We just adopt it. We just say, okay, solutions may not be regular. That's fine. We define wave number according to the regularity level or intermittency level. That's it. Okay, so so that's 3D case. And we mentioned that we're able to treat supercritical case, and 2D Navier-Stokes it's subcritical. Indeed, apply this approach or this framework, we're able to get some results in 2D as well, which improves some classical results. So now back to 2D Navier-Stokes equation. So they're corresponding to the kappa D, the Kolmogorov wave number. There is a criterion wave number for 2D Navier-Stokes equation, and that's the one physicists use. Okay, so we define a dissipation of planes to phase. That's a Laplace. And there's the criterion number. And again, this intermittency dimension for 2D flows, d is from 0 to 2. That is correct. Okay. And in the earlier background part, we said that there is estimate of the determining modes for 2D Navier-Stokes in terms of Grashof number, but there was no estimate of determining modes in terms of criterion number, although this is the one physicists use. Okay, so it would be nice to have some estimates of the determining modes in terms of criterion number. So then we applied the approach here. We construct some wave number for 2D Navier-Stokes equation. Again, we separate the two cases, and there is a wave number in terms of a critical norm based on L2. So I'm not going to write details. And when d is away from 0, a wave number in terms of infinity. Okay. Instead, it's one. I'm going to just omit the details. So it's a similar definition with those wave numbers here, okay? But in their own critical norms, okay? But that's not the final definition. We're going to optimize space because in 2D we have global regularity. So with those definitions, we take a lambda star. It's the minimum of the wave number and the time average. So what that means, right? So if we draw a picture here, say that is the lambda defined there. Since it's bounded, solutions are bounded, so all of the norms have upper bound, so it makes sense to talk about the average, which should be finite. So that's the average. And the star is the minimum. So we take it like this. All right. Okay, so that is the star. So we showed that the lambda star it's a recent result. Star is determining wave number, again in the same things. Second, we have the estimate. The wave number pointwise. Okay, so now it's not average, it's pointwise. And moreover, that is a Grashof number. Okay, so you can see that the result for 2D flow is better, and we get a pointwise estimate on the determinant wave number. And when D equal to 0, that recovers a classical result of a TT earlier on the boards. Okay. Okay, very good. I think I have a few minutes to maybe talk about a little bit on the predictions number 2 and 3. So what about the Kolmogorov physics laws number 2? So number 2 is an energy spectrum, mostly it's numerical study here. Okay. Number 3 is anomalous dissipation. That's an open question. Okay. However, it's open for the actual PDE, but it's a soft for the Dowdic. Navier-Stokes equation again by Alexei and Susan Freilander and Natasha. Okay. Okay, so we get the idea, right? Maybe it's not a bad idea to study simplified models when the dynamic is really complicated. Okay. So here, very quickly, I just want to see some another important fluid model. It's the magnetohydrodynamics. So we started to look at the MHD a while ago, and we really interested in the anomalous dissipation problem. But again, the real PD, the real dynamics, it's very challenging. It's even more complicated than pure fluid turbulence. So here we look at the Dowdic models. So here, that's the problem we are interested in. Okay. And to have a answer to the problem here, we need a good understanding of stability of fixed point. So we are able to find fixed points in the ideal case exactly, okay, explicitly. It's a set of a 2-parameter family. Even at this level, it's very hard, okay? And we don't know much about the stability of the fixed points, because here we have a set of fixed points. It's not unique. It's different from the Dowdic Navier-Stokes equation. Okay. So if I just so they're all open. Okay. So to illustrate it briefly, so the set of the fixed point in one situation we have both forward and backward energy cascade in the system. The fixed point sets are not even bounded; they are on hyperbola. Okay. So it's highly non-trivial here. Okay. So what we can do is so what we can show is that we can verify the energy spectrum. Again, that's just the numerics. Okay. It's recent results. Some classical type of results we can show blow up based on the intermittency level. Okay, and let's see a recent result with Susan Craigland. Also, we studied uniqueness and uniqueness problems. And here we found a sharp threshold. When the intermittency is less than 1, we construct non-unique Larry-Hopf solutions. When the intermittency is greater than equal to 1, then we have uniqueness. Okay. Yeah. So, but what we know, it's again it's really limited. What we can do here is limited. There are lots of open questions here in terms of the understanding of turbulence. Okay. Okay. So, just to summarize here, we did we got some results, and we realized that intermittency has to be into the game. Okay, I'll stop here. Thank you.
Are there any questions?
So if I just take decay in 3D Navier-Stokes on the torus, do you expect that? What do you expect the intermittency dimension to be? I mean, does it strongly depend on what on how you started, or?
So there are experiments that show that intermittency is very close to 2.7. Maybe that's the number E. It's an irrational number.
And in that case, so the number of determining modes, is it? I couldn't quite tell. Is it always finite?
2D, yes, but
3D can.
3D, no, we don't know, right? Because the wave number can blow up if the solution blows up.
So your 2.7 was for credit.
How do you know the numerics are reliable?
That's a good question, actually. I don't trust numerics myself very much.
They run different initial conditions and get the same kind of answer. That's what makes it happy.
Right. You give random. You can give random initial data and run as many times as you want. And see if the results are consistent.
I also read about the same 2.7. It seems to be a magic number.
The intermittency dimension.
Yeah. In 3D.
In 3D.
Right. In 2D, you know, I don't know.
In 2D data, what do they know?
So as far as I understand, there is still a debate whether 2D flows can be intermittent.
I'd like to thank the speaker again for a remarkable story.